Hello everyone and welcome back to the Regents Chemistry Review Series. In this video, we're going to talk about organic chemistry. So, organic chemistry is defined as the study of carbon-based compounds. So, carbon is like the backbone, the foundation of organic chemistry. However, organic compounds can also contain hydrogen, oxygen, and nitrogen. So, these are also very common elements in organic compounds. But some of the properties of organic compounds is that they do have carbon, and remember that carbon has four valence electrons, which means it can make four more bonds, so covalent bonds. So you can share, carbon can share those four electrons to make four covalent bonds. So organic compounds in general have very low melting points. They are poor conductors of electricity because it's very hard for them to either dissociate or just like have charged particles moving around, and they also are very slow reactors. So organic reactions are extremely slow compared to the chemical reactions. So the hydrocarbons are the simplest type of organic compounds out there, and these type of organic compounds have carbons combined with hydrogen atoms. So carbon atoms combined with hydrogen atoms, and these are the only two elements that are found in hydrocarbons. So if you also see oxygen and nitrogen or like anything else in any structure, then that's a different type of organic compound. It's not a hydrocarbon. So there are three types of hydrocarbons. We also call this the homologous series, which is the word that is used in the table that gives you these three types of hydrocarbons. So homologous series, just so you are not confused about this word. So the first type of hydrocarbon is an alkane. So this is kind of like a simple type of hydrocarbon where we have all single bonds. So one example of that is C2H6. So if we want to draw this, it's going to be two carbon atoms single bonded to each other, and then we have six hydrogens. So that means each carbon can have three hydrogen atoms. So in total, if you count, each carbon has four bonds. And yeah, that's like the maximum number of hydrogens that the two carbon atoms can have. Compared to alkene, which have so they have at least one double bond in their structure, which means they do not have the maximum number of hydrogen atoms. So here's an example. Now we have C2H4. If I try to draw this, in this case, the two carbons are going to be double bonded to each other because we only have four hydrogens. So that means each carbon can only be bonded to two hydrogens. So now if you once again count the bonds for each carbon, each one of them has four bonds. Next up, the last type of hydrocarbon is an alkyne. So alkynes have at least one triple bond, and again, they do not have the maximum number of hydrogens. So here's an example. We have two carbon atoms and only two hydrogens. So if we put these two hydrogens on the side, and let's say we just make a single bond between the two carbons, you'll notice that each carbon now only has two bonds. So that means they need two more bonds. So to add those two bonds, we're going to have to make a triple bond between the carbon atoms to make sure that they have four bonds. So these are your three types of organic compounds. Now, some other words that we use for hydrocarbons are saturated and unsaturated. So saturated hydrocarbons are the ones that have maximum number of hydrogen atoms. So this is only possible if we have single bonds. So alkanes are examples of saturated hydrocarbons. Unsaturated hydrocarbons are the ones that do not have maximum number of hydrogens. So that is if they have a double or a triple bond. So both alkenes and alkynes are examples of unsaturated hydrocarbons. So when it comes to naming hydrocarbons, here we are given a molecule, but let's talk about some of the very basic steps or rules that we follow. So the first thing that you're going to do is we are going to identify the parent chain. And remember, parent chain is the longest continuous carbon chain. So in this case, if we want to identify our parent chain, it's going to be this one right here. because this chain is the longest continuous carbon chain. So if you count the number of carbon atoms, we have 1, 2, 3, 4, 5, 6 carbon atoms in this one. So the next thing that we're going to do is we are going to number the carbons on the parent chain. As we are numbering the carbons on the parent chain, we want to make sure that the first branch that we see must be on the smaller number of carbon possible. So here's what I mean by that. If I number this carbon chain from this side, 1, 2, 3, 4, 5, 6, I notice that the first branch that I see is on carbon number 3. Right? And the second branch is on carbon number 5. However, if I go ahead and number this branch from the other side, so if I number it from this side, so 1, 2, 3, 4, 5, 6, now my first branch is going to be at carbon number 2, and the second branch is going to be at carbon number 4. So because we want our first branch to be at the smallest number of carbon, that means in this case, we are going to number from right to left. So let me go ahead and erase the other one. Okay. So once we have numbered the carbon chain, our next step is going to be to name. No. What happened? Okay, let's go ahead and name the parent chain. So when we are naming the parent chain, first of all, we have to identify if it's an alkane, alkene, or alkyne. So in this case, we see all single bonds between the carbon atoms. So that means we have an alkane. So we are going to end the name with an ane, A-N-E. Okay, the next thing that we're going to do is see if there is a double or a triple bond present. If yes, we need to identify the location. We do not have a double or triple bond in this case, so we don't have to worry about it. Then we have to add the prefix of the parent chain to indicate the number of carbon atoms in the parent chain. So your prefixes are given in table P. So the prefix for 6 carbon atoms is a hex. So this is going to be hexane. All right, now that we have numbered the parent chain, our next step will be to name the branches that we see here. So when we are naming the branches, we're going to end their name with a YL. And for their prefix, we just put the prefix for the number of carbon atoms. If we have more than one branches, then we are going to need to use the prefix for more than one number of branches. So for example, if we have 2 of the same branches, we're going to say we have di, whatever that branch is. If we have 3 of the same branches, that will be tri of that branch. And if we finally, we do have to indicate the location of the branch at the parent chain. So let's first go ahead and see what branches do we have here. So we see this branch right here that has 1 carbon atom. So the prefix for 1 carbon atom is going to be meth. And we're going to end this with a YL. And then we also see this branch right here, which also has 1 carbon atom. So the prefix for 1 is meth, and we're going to end that with a YL. So as you can see, we have 2 methyls. So we're going to say that we have dimethyl in the name. So as of this moment, the name of our compound is dimethylhexane. The only thing that is left now is to tell where are the branches specifically. So we have our branches at carbon number 2 and carbon number 4. Make sure that you put the comma in between of the 2 numbers, and then you are going to connect the numbers with the words using that little dash. All right, so this is how we name the hydrocarbons. So let's do some more practice. So here we are given this compound, and we're going to go ahead and first of all identify the parent chain. Remember, parent chain is supposed to be the longest continuous carbon chain. So as we are identifying that chain, we can start from here and like keep going. You do not stop at this carbon, because remember that this carbon can continue going up. We cannot have a branch on the terminal carbon. This is a very, very important rule to keep in mind. We also discussed this in class. There is no branch on terminal carbon because we can technically keep going and make that carbon a part of our parent chain. Okay, so in this parent chain, we have about 1, 2, 3, 4, 5, 6. Wait, I lost my count. 1, 2, 3, 4, 5, 6, 7. We have seven. We have seven carbon atoms. So the prefix for 7 is hept. And then, as you can see, we have some double bonds here. So we are going to end this with an ene. Now, the reason why I left some space in between the hept and the ene is because we have to put the location of the double bonds. So let's number our carbon chain. So because now we have the double bonds as well, so we're going to treat the double bonds the same way we did the branches in the previous one. So either your double bond or the branch, whichever one comes first, has to be on the lowest number of carbon possible. So we're going to start from this side now. 1, 2, 3, 4, 5, 6, 7. So we notice that we have our first double bond at carbon number 1, and we have the second double bond at carbon number 3. So we are saying it's hept 1, 3 ene. Now our name indicates that we have 2 double bonds, but then to name this correctly, instead of just saying ene and to kind of reiterate that we have 2 double bonds, we are going to say diene. So first we mentioned 1, 3 to indicate that this is the location of the 2 double bonds, and second we're going to end that with diene to indicate that we have 2 double bonds. Okay, so this was your parent chain. Now we are left with the branches. We still need to put the location of the branches. So I see one branch at carbon number 3, one at carbon number 5. So this one is a methyl. This one is also a methyl. So that's going to be dimethyl. And then we put the location, which as we just said is going to be 3, 5 dash. Okay, so let's look at the next compound. Once again, identify the parent chain, which is going to be this one over here. So it has 1, 2, 3, 4 carbons, all single bonded. So that's just going to be butane. And then we see that at carbon number 2 and 4, in this case, it doesn't matter whether you number it from this side or the other side, because you're going to end up with your 2 branches at carbon number 2 and 3 always. So at carbon number 2 and 3, now this one is slightly different, because instead of having a carbon based branch, you see 2 bromines. So this one is a halocarbon. And when we are naming halocarbons, we are going to just put, so this is a bromine, so that will be named as a bromo. And because we have 2 of them, we are going to say dibromo. So this is 2, 3 dibromobutane. All right. So that was naming hydrocarbons. What if we are asked to draw hydrocarbons? There are different type of formulas that we need to be aware of. The first one is your molecular formula, which is just like simply the chemical formula. It gives us the number of atoms of each element in a compound. Then we have the structural formula, which is where we draw like the extensive structures. We include all of the bonds, all of the atoms, everything. Then we have a condensed formula. So condensed is where we take out the bonds from the structural formula but write everything else to indicate the basic structure. And finally, the skeletal structure, which is not a part of the Regents curriculum, but it's still like the fun structure to draw. So this is where we only draw the bonds between the carbon atoms. That's it. Everything else is kind of up to the reader's understanding of the skeletal structures. But if you see something like halogens or like oxygen, nitrogen, those things you do have to write in the structures, but carbons and hydrogens we do not write. Okay, so let's look at some examples. So maybe I'm gonna try to think of a compound. Let's take the fancy one. So maybe do 2 fluoro 3 ethyl pentane. All right, so let's first go ahead and draw the structure for this compound so that it's easier for us to write the molecular formula. So for the structure, we know that this is a pentane, meaning 5 carbons, all single bonded. So 1, 2, 3, 4, 5, all single bonded. Now we know that at carbon number 2, we have a fluorine. So let's make this a carbon number 2 and make a fluorine there. And we know that at carbon number 3, we have an ethyl branch. So at carbon number 3, let's make a branch with 2 carbons. So now all that we have to do is fill in the hydrogens while taking into account the number of bonds for each carbon, right? So the first carbon needs 3 hydrogens. The second carbon only needs 1. Third carbon only needs 1. Fourth carbon needs 2. And the fifth carbon needs 3. Okay? And then if you look at the branch, the carbon in the middle needs 2 hydrogens and the carbon at the end needs 3 hydrogens. So this is your structure. Now, when we are writing the molecular formula, it's just going to be counting the total number of carbons, total number of hydrogens, and then just a fluorine. So we have 1, 2, 3, 4, 5, 6, 7 carbons. So that's going to be C7. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 hydrogens. And then 1 fluorine. So this right here is your molecular formula. Okay? So then if we have to write the condensed formula using this using the structural formula, that is going to be CH3 CH2 F and then CH. And whenever we are writing the condensed formula with a branch, we can make only one bond to indicate the branch. So this is now going to indicate the branch, which is going to be CH2, CH3. Okay, and then we continue with carbon number 4, which was CH2, and then the last carbon was CH3. So as you can see, all that I've done is taken out the bonds and just like written the number of hydrogens and everything else that we have for each carbon. Okay, and then lastly, for your skeletal structures, we have to indicate the location of each carbon, which is represented by a corner in the line. So it's kind of like a zigzag structure, and each corner represents a carbon atom. So we can start with carbon number 1, which is the first corner, and then we make a line to represent second carbon, third carbon, fourth carbon, and fifth carbon. So this is our parent chain. Okay, we normally do not draw the dots. I'm just making the dots to kind of help you all visualize this and count with me, but we don't draw the dots. It's just a line like this. Okay, all right, so the next thing that we have to do is make our branches. So at carbon number 2, we're gonna go ahead and make a fluorine, and then at carbon number 3, the branch is going to be 2 carbons. So here is the first carbon and here's the second carbon in our branch. Okay, so that is the skeletal structure of this formula. So let's look at some other organic compounds besides the hydrocarbons. So we are given the functional groups for the rest of the organic compounds in table R. So one type of organic compound is an alcohol, and it has a functional group of OH, so a hydroxyl group in the formula. So these are the most soluble organic compounds. When we are naming them, we name the prefix based on the number of carbon atoms in the parent chain, and then we use the suffix ANOL. So that indicates that this is an alcohol. And then we do have to indicate the location of the OH unless the OH is on the terminal carbon. So terminal means first or last carbon. So if the OH is on the first or last carbon, then we do not need to put the location, otherwise we have to. For example, here we have 2-pentanol. So if we have when we are naming the compounds, if we have 2 hydroxyl groups or 2 OH groups, then we say diol or we say dihydroxy, but diol is like a better way to say this because we normally end the name with ol. And then if we have 3 OH, then we say triol, and so on and so forth. So let's go ahead and try to draw the structure for 2-pentanol. So first of all, we see the prefix pent, and pent means we have 5 carbons in the parent chain. So 1, 2, 3, 4, 5. And then it says we have the ANOL, means we have the alcohol or the hydroxyl group at carbon number 2. So at carbon number 2, make the OH. And then all we have to do is fill the hydrogens for the rest of the carbons. So the first carbon needs 3, the second one needs 1, third needs 2, fourth needs 2, and fifth needs 3. So there you go. You have the structure of your alcohol. Then we have an organic acid. So this is the functional group for an organic acid, which is normally whenever you see COO, that means carbon is double bonded to one oxygen and single bonded to the other oxygen. But in this case, we also have the hydrogen at the end, so that means this oxygen is an OH instead of just oxygen. So whenever you see, and on this side, you're going to have a carbon chain or just a hydrogen, depending on what organic acid we are looking at. So the functional group, this one always occurs at the terminal carbon. So that means when we are naming this, we don't have to include the location of where the functional group is. And because this is an organic acid, these compounds do have acidic properties. So let's look at an example. We have CH3COOH. Let's try to draw this. So we have this carbon. We can first go ahead and make like the functional groups. That's going to be C double bonded to one oxygen, single bonded to OH, and then on the other side we see a CH3. So CH3. Okay, and then we are going to name this. So in this case, we have 2 carbon atoms. So the prefix for the 2 carbon atoms is going to be eth. So that's going to be eth, and then the suffix for all of the organic acids is enoic acid. So this is going to be your ethanoic acid. Okay, so that's the rules for naming. Prefix is number of carbon atoms, and then suffix is enoic acid. All right, so next up we have an ester. So here is the functional group for the ester. If we try to draw this, once again it's COO, so that means carbon is double bonded to one oxygen, single bonded to another oxygen, and then that oxygen is connected to a carbon, which can have something else connected to it, and this carbon can also have something else connected to it. So esters kind of occur in the middle of the carbon chain, and they actually look very different. Let's try to draw this one that we have. So first of all, we can go ahead and draw the functional group. So we have carbon double bonded to an oxygen, single bonded to the other oxygen, and then we have a CH3 on this side. So that's going to be carbon with 3 hydrogens, and then we have CH2 and CH3 on this side. So CH2 and CH3. Okay, so when we are naming these type of compounds, we are going to draw a line between the single bonded oxygen and the double bonded oxygen, because that's going to make it easier for us to name them. So let's draw a line between the single bonded oxygen and the double bonded oxygen. So the single bonded side is going to end with the YL, and then we use the prefix for the carbon as the prefix for the YL. So because we only have one carbon here, so the prefix for one carbon is meth. So that's going to be methyl. And then we end this with the second part. So for the double bonded oxygen, the prefix for 3 carbons is going to be prop. And then we end that with anoate. Okay, so this ester is going to be named as methyl propanoate. In a little bit, when we talk about organic reactions, we are going to look at how our ester is made. So it's kind of going to make a little bit more sense that which part is coming from which type of compound. So next up, we have ethers. Ethers have this functional group. They just have an oxygen in the middle of the chain. So here's an example. Let's try to draw this. We see an oxygen in the middle, so right here. And then on one side of oxygen, we have CH3. On the other side of oxygen, we have CH2 and CH3. So basically, it's kind of like we have 2 carbon chains on both sides of oxygen. So we end the name of this with an ether, and then we basically just have to name both chains on the 2 sides of the ether. But the thing to keep in mind is that we have to alphabetize those chains. So in this case, we see that on the one side of the compound, we have an ethyl branch. On the other side, we have a methyl branch. So we are going to name this as ethyl methyl ether. Okay. Next up, we've got ketones. So ketones look something like this. So in this case, you see this carbon with an oxygen. That means we have a carbon double bonded to an oxygen, and then you see you have like a carbon or just like an R group on both sides. So let's go ahead and draw this one. We're gonna make the functional group in the middle, and then on one side we have CH3, on the other side we have CH3. So when we are naming ketones, we use the prefix for the number of carbon atoms. So in this case, we have 3 carbon atoms, so the prefix for that is going to be prop. And then we are going to end the name with, well, that is wrong. It should be ended with anon, A-N-O-N-E. So this is going to be propanon. And then we do have to indicate the location of the carbon double bonded to oxygen. So in this case, it's at carbon number 2. So that's going to be 2-propanon. Then we can also have aldehyde. So in this case, once again, we see carbon written with an oxygen. So that means it's double bonded to the oxygen. And we have hydrogen on one side. And then on the other side of the carbon, we most likely have a carbon chain. So this functional group occurs at the terminal carbon, meaning the first or the last carbon. So we do not need to include the location. So here's an example. Let's draw it out. So the functional group first, carbon double bonded to an oxygen. Then we have hydrogen here. And then in this case, we have CH2 and CH3. So when we are naming this organic compound, the rule is prefix is for the number of carbon atoms, and then we end that with anal, A-N-A-L. So in this case, we have 3 carbons, so it's going to be propanol. Okay, so the last 2 types of organic compounds that we have are amines. So amines have a nitrogen with 3 bonds, and they normally occur in the middle of the chain. So here we see that we have 3 carbon atoms. So carbon number 1, 2, and 3. Now notice how the NH3 in the condensed formula is written right after the second carbon. However, you cannot disconnect the carbon chain to make the nitrogen in the middle of the carbon chain. So what you're going to do is that nitrogen, the NH2, is going to be a branch on the second carbon. Okay, and then remember that for nitrogen we always include a lone pair of electrons, because nitrogen makes nitrogen has 5 valence electrons. It makes 3 bonds, so the 2 electrons are going to be the lone pairs. Okay, so then we just have to fill the hydrogen. So CH3 for the first one. It should not be CH2 for the second one. It should just be CH for the second one. And then we have CH3 for the third. So when we are naming this, it's going to be, the rules are that your prefix is just based on the number of carbon atoms, which is prop in this case. And then we end that with anamine. So anamine. And then of course we have to put the location of the nitrogen. So that's going to be at carbon number 2. So lastly, we have the amide. So this one has a carbon double bonded to oxygen, and then we have nitrogen, which has 2 bonds. So normally it's 2 hydrogens, but sometimes it can be 1 hydrogen and then something else. And then the carbon also has a carbon chain on the other side. So here we have an example of an amide. So let's draw the functional group first. So carbon double bonded to oxygen, and then it's connected to NH2. Don't forget the lone pair on your nitrogen. And then next to this carbon we have CH2, CH2, and then CH3. So when we are naming this, the prefix is again based on the number of carbon atoms. So that's going to be 1, 2, 3, 4, which is bute. And then we end this with anamide. We do not need to put the location of the functional group. That's because this one occurs at the terminal carbon. All right, so next up, we can be asked to draw the isomers of organic compounds. So isomers are the compounds that have same molecular formula and the same percent composition, meaning they are made of the equal mass of each element. But they have different structural or condensed formula, and because of that they are going to have different properties. So when we are drawing the isomers, you need to count up the total number of atoms and then put them in different order. Okay, so let's look at some examples. So here we have C5H12. Let's try to draw some isomers for this. So first of all, we can make a carbon chain 1, 2, 3, 4, 5 with 5 carbons, and then see how many hydrogens we can put with this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this is your one structure for C5H12. Now if I want to make a different structure but still make sure that we have same number of carbons and hydrogens, what you can do is put a branch on this compound. So remember, don't put a branch on the terminal carbons. So maybe I can go ahead and put like 4 carbons in the parent chain and then put 1 branch on carbon number 2, like a CH3 branch. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens again. Okay, let's look at a different example. So we have C3860. So in this case, we can this one has a oxygen, so that means we're gonna have to look at the different functional groups of the carbon atoms. The different functional groups, meaning different types of organic compounds. So maybe think about what are the different types of organic compounds that have an oxygen. Maybe we can think about an aldehyde. Let's start with an aldehyde. So we need 3 hydrogens, so 1, 2, 3. And aldehyde has a double bonded oxygen, and it also has a hydrogen. And then we have 1, 2, 3, 4, 5. Okay, that's perfect. So we have 6 hydrogens, 1 oxygen, 3 carbons. Now let's think of a different example. What if we try to move this carbon double bonded O to the center? That's going to make it a ketone. So in that case, we have 1 carbon on both sides, and both of them have 3 hydrogens. There you go. So that is a good example of these two are good examples of isomers. So the first one is an aldehyde with 3 carbons, so that will be a propanol, and then the second one is going to be propanone because it's a ketone. Okay, all right. So next up, let's look at the what happened here. Oh, so let's talk about the organic reaction. So these are different reactions that involve organic compounds, and they're much slower compared to the chemical reactions. So one type of organic reaction is substitution. Whenever you are asked to define a substitution reaction, make sure that you write this part. Make sure that you are saying that we have a saturated hydrocarbon combining with a halogen. We are making a halocarbon and an acid. Don't just say something is getting substituted by the other thing. Okay, make sure that you know what it looks like. So this is an example of your substitution reaction. So as you can see, we have a hydrogen that is leaving this compound and combining with one of the chlorines, and then the one chlorine that is left is taking the place of that hydrogen. So we get a halocarbon and an acid. And then we have an addition reaction. So once again, make sure that you memorize this equation. We have an unsaturated hydrocarbon which combines with a halogen and make a halocarbon. So here is an example. So what's going to happen is that this double bond is going to break, and we'll have the empty spots left on these two carbons. So those empty spots are going to be taken by the two bromines. Okay, so that's how we get a halocarbon. Okay, so other types of organic reactions, we have fermentation. So fermentation is when we have any type of sugar combining with yeast or just any type of enzyme, and they produce alcohol and carbon dioxide. Sometimes you might get a reaction equation on the Regents exam where they don't give you yeast or enzyme, because whenever you see yeast, that's kind of like a very easy answer that this is fermentation. So sometimes to confuse you, they don't include the yeast in the reaction, but still know that if you have a sugar converting into alcohol and carbon dioxide, it is fermentation. So this is kind of what the equation looks like. Then we have saponification. This is the soap making reaction. So it's in fancy words, it's defined as the hydrolysis of a base by hydrolysis of a fat by an acid. So we take any fatty acid, we combine that with a base, and we get soap and glycerol. So the reason why it's called a hydrolysis is because we break the bonds in the fatty acids in the presence of water. So this reaction, whenever we are breaking bonds in the presence of water in any reaction, it's called hydrolysis. So lastly, we have esterification. So in an actually not lastly, but esterification is the reaction to make esters. So in this case, we combine an organic acid with an alcohol, and that makes an ester or water. So let's think about an example for this. So think about any ester, any organic acids. Organic acids are supposed to have a carbon double bonded to an oxygen and an OH. So let me just go ahead and put maybe another carbon here and make this. So this is going to be ethanoic acid. And then let's think about an alcohol. So alcohols are supposed to have an OH. So maybe do like 3 carbons. So 1, 2, 3. Put an OH over here. And then put your hydrogens for the rest of them. So this is going to be propanol. Okay, so now what happens in esterification is that the OH from the ethanoic acid and the hydrogen from the alcohol, these two things are going to combine, and they are going to make water in the products. So now that water is gone, everything else that is left in this reaction is going to be together. So this part and this part is going to combine to make the ester. So we are left with this carbon, like these two carbons, a CH3 and a carbon double bonded to oxygen. And then from the alcohol part, we have that oxygen left. And then with the oxygen, we have 3 carbons. So 1, 2, 3. 1, 2, 3. So this is your ester. When we have to define this, remember that this part is coming from the organic acid, and the prefix for organic acid was eth. So this is going to be eth, and because it's the double bonded part, so we were ending that with anoate. So that's going to be ethanoate. And then the part with the single bonded should have the same prefix as the alcohol because it's coming from the alcohol. So that's going to be propyl. So this one is propyl ethanoate. All right, so the last type of reaction that we want to talk about is polymerization, and we can have 2 different types of polymerization. We can either have condensation polymerization, so this is when we have several monomers that are combining to make a polymer, and they also make water with the polymer. So here's an example. We have these monomers combining, and then they are releasing the OH and hydrogen to make water with the polymer. So polymer is kind of just like a lot of monomers combining to make a bigger thing. And then in case of addition polymerization, it's just several monomers that are combining to make a polymer. That's it. So sometimes you get an equation like this where you're given a formula and they write X with that, meaning a lot of these things combining, and then they give you a different formula which is then going to be the monomer, and they write the X in the subscript to represent that, you know, more than one of the monomers. So that should be an example of your addition polymerization. Last thing that you need to know about polymers is some examples of natural and synthetic polymers. So your natural polymers are starch, cellulose, proteins, and some examples of your synthetic polymers are nylon, polyethylene, plastic, etc. All right, so that was organic chemistry. I will see you in the next and the last one.